Hello guys, welcome back to Clinically Clear. So today we'll cover the parameters of a screening test. So basically, a person can have a disease, a person may not have a disease. Screening test can come positive, screening test can come negative. Okay. So I'll construct a 2 by 2 table, disease always on top, disease present, disease absent, test comes positive, test comes negative. Okay. Second rule is, see which are the good ones. If the person has a disease, person's test comes positive, it's good. That means the test is right, true positive. Person does not have a disease, test comes negative, true negative, that's good. Person does not have the disease but test comes positive, false positive. Person has the disease, test comes negative, false negative. Okay, this is how you construct a 2 by 2 table. Now remember, first we take columns and never cross the sides. By what I mean is, I'll tell you. See, first is sensitivity, okay, which is the most important factor. The ability to correctly identify those who are diseased. So those who have the disease, to ability to correctly identify it is known as sensitivity. Is the most important. That's the whole point of a screening test, to detect those who have the disease. Sensitivity is true positives divided by total number of disease positive into 100. Into 100 is just for the sake of percentage. Just remember this part. True positive divided by disease positive. Basically, true positive divided by true positive plus false negative. Same thing. So, true positive divided by disease positive. That is sensitivity. So, you're talking about true positives when it comes to sensitivity. And remember something, this statement you'll see in each of these parameters. Whenever I'm telling probability of something something out of something something, the out of is always for the denominator. Example, here, true positive out of the diseased, out of disease present. Disease positive means the disease population, the people who have the disease. So the probability of being tested positive out of the diseased population, those who have the disease, is known as sensitivity. That is also one more definition. Okay. So what does it mean if a sensitivity is very high? That means that, let's say it's some 98% or something. 98 sensitivity means out of 100 people who have the disease, if I do the test, 98 will come positive, which is a true positive. Okay. And so that means a highly sensitive test, if you get a positive result, that means you most likely have the disease. This is sensitivity. Specificity means immediately you should think of true negatives. Once again, come here. True negatives. So, true negatives out of those who do not have the disease. So, what is specificity? Ability to correctly identify those who do not have the disease. Who don't have the disease? The negative, the people who, the disease negative people. Correctly identify means true negative. So, true negative out of the disease negative population, those who don't have the disease. So, true negative out of disease negative. So, the probability of being tested negative out of the healthy population. Disease negative means what? They don't have the disease. They are healthy population. That is specificity. Understood? False positive error rate. False positive error rate. Basically, here you can see false positive. Again, we're never crossing the side. Sensitivity also we remained on this side. Specificity also we remained on this side. False positive error rate also we remain on this side. So, false positive error rate, number of false positive divided by those who do not have the disease. Understood? So, false positive divided by disease negative. So, probability of being tested positive or being falsely tested positive out of the healthy population. Out of is always for denominator. Out of the healthy population, that is false positive error rate. Now, if you think about it, Fp by D minus is false positive error rate. Tn by D minus is disease negative is specificity. If you add these two, you get D minus by D minus, that is nothing but 1. So, you can also say false positive error rate is nothing but 1 minus specificity. 1 minus specificity is false positive error rate. So, if a test is highly specific, false positive error rate will come down. Similarly, for sensitivity, if a test is highly sensitive, false negative error rate will come down. Because sensitivity, we are looking at the number of true positives. So, more the true positive, less the false negatives. Specificity, we are looking at the number of true negatives. More the true negatives, less the false positives. Understood? So false negative error rate, Fn by d plus. Again, we're not crossing the side. Remember, false negative, Fn by d plus. We're never ever crossing the side. We're remaining in the same side. False negative divided by total disease population. So the probability of being tested falsely negative out of the disease population, out of, always for denominator is disease population, out of the disease population. Okay, these four things you understood, right? Next, coming to, see, we'll assume there's a screening test, that is constant sensitivity of 90%, constant specificity of 90%. Just remember constant sensitivity and specificity. You have an epidemic in a region, early stage, very early stage, but you've identified it to be an outbreak. Because it is in the early stage, prevalence is low. Total number of cases is very less, very few cases. But incidence is high. Why? Because now the epidemic is spreading. New cases are coming up. So incidence is high, but prevalence is still low. Why? Because we are in the early stage. Total number of cases are less, very few, rare cases. So, but because incidence is increasing and it is an epidemic, you are doing extensive screening efforts. You're screening everyone. So when you're screening everyone, but the prevalence is low, very few cases, most people being screened are healthy, disease negative. So you have a lot of disease negative people now. So before you had a specificity of 90%. If a specificity is 90%, I told you false positive error rate is 1 minus specificity. Basically 100% minus specificity in percent. So if specificity is 90%, false positive error rate is 10%. Okay, and it is constant for a given test. So before this epidemic, I had false positives, the number of false positives divided by the total number of healthy people before. Now I am screening way more number of people. So now I have false positive mu and way more healthy people. Why do you have a lot of healthy people now? Because most of the people you're screening are healthy because the prevalence is low, still in the early stages. So now what happens if I take this side, a high value has come. So now what happens, the number of new false positives increases. So that is why when, this is a bit of a weird statement, when the prevalence is low but the incidence is high, the number of false positives will increase for a test with given specificity. Understood? But eventually what happens, epidemic spreads everywhere, prevalence becomes high. So the total number of cases becomes high. Screening efforts are still high because it is an epidemic. So now what happens, you're testing everywhere, all of them have disease. So the number of disease cases are increasing because the prevalence is high. And sensitivity is fixed. What is sensitivity? True positive divided by those who have the disease population. So true positive before by disease present before is equal to true positive mu divided by disease positive mu, because sensitivity is constant, and disease present mu, because of the high prevalence. Obviously high prevalence means disease positive mu is more. Common sense, bro. See, whenever the prevalence is high, the number of true positives has to increase. Lot of cases, so the number of true positives has to increase. When you have a lot of cases, most of the people you're testing that's coming positive will end up being a true positive. Understood? So when the prevalence is high, true positive increases. Important. Even in an epidemic, when the prevalence is lower, rarer the disease, even if it has a higher incidence, then the false positives will increase, and more common a disease is, the screening test will produce more of true positives. Okay, this is a bit of a weird thing. Then come into something known as positive predictive value and negative predictive value. Now these are to assess the diagnostic power of a test. Both positive predictive value and negative predictive value have to be high for it to be a good test, okay, good screening test. This time we'll take rows into account. Again, never ever cross the side. Listen to me, never cross the side. Same thing, other than that everything same, disease on top, disease in it. You have something known as positive predictive value and negative predictive value. Positive predictive value, we are looking at the true positives, okay. We are predicting how many true positives it is getting out of all the test positives. So true positive remain on the same row, true positive out of the tested positive. So what are true positives? True positives are the one having the disease, right? So the probability of having the disease out of those tested positive is positive predictive value. Understood? And positive predictive value is obviously proportional to prevalence. Because if prevalence is more, I told you just now, true positives increase. And if true positives are more, positive predictive value is increased. Very important. Higher the prevalence, higher the positive predictive value. Most important factor for positive predictive value is prevalence. Most important factor for positive predictive value is prevalence. Very, very important. Because when prevalence of a disease increases, true positives increase. So probability of having the disease out of those tested positive is negative. So very, very common disease, and 100 people have been tested positive, then 99, 98 of them will be actual true positives. Understood? So that is positive predictive value. Similarly, negative predictive value. True negatives out of those who have been tested negative. So probability, who are true negatives? True negatives are healthy. Probability of not having the disease or probability of being healthy out of those tested negative. Probability of not having the disease out of those tested negative is negative predictive value. Positive predictive value is directly proportional to prevalence. Negative predictive value is inversely proportional to prevalence. Okay, understood? So basically that's it, bro. Here you'll write sensitivity, here you'll write specificity, here you'll write false positive exam error rate, here you'll write false negative error rate. And if you're looking in terms of rows, then this row you'll look at positive predictive value and this row you'll look at negative predictive value. That is how from a 2x2 table you'll get all the screening parameters. Then coming to some examples of screening tests under National Health Program. Under National Tuberculosis Elimination Program, sputum smear examination is this screening test. Under National Vector-Borne Disease Control Program, malaria is a good screening test. Under NPNCDS, National Program for Non-Communicable Diseases, for diabetes, you have fasting blood sugar, postprandial blood sugar, urine sugar. For cervical cancer, you have Pap smear. For colon cancer, you have fecal occult blood test. Now, why I put star for colon cancer, fecal occult blood test is in colon cancer, screening test and early diagnosis makes a huge difference in the prognosis. This fecal occult blood test, if you diagnose small amounts of blood in the stool, early stages, then colon cancer prognosis improves by a huge, makes a huge difference. And mammogram for breast cancer, all this is NPNCDS. Under National Program for Control of Blindness and Visual Impairment, you have school eye screening camps for refractory errors. Under NACO, National Age Control, you have HIV, ELISA, TriDot, all that stuff. Some 2-3 you remember more than enough, just to give an examples for the screening test. That's it for screening. Thank you for watching.